Hello and welcome to the first of the lectures in this third week under the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered and over the NPTEL platform. In the lectures during the last week, we have seen that we could introduce a few algebras on the set of fuzzy sets. We saw that min and max, this combination of operations, they played an important role. Also, we should remember these were possible because of the properties that we could inherit from the structures that were already available on the 0-1 interval. However, we were left with a question as to what about the other interpretations of conjunctions? Are they still useful? Note that the Lukasiewicz pair of operations, they came very close to giving us a lattice. In this lecture, we will look at extracting the properties that are required of a fuzzy conjunction towards giving an axiomatic definition of what one generalization of fuzzy conjunction at least should be. This particular generalization is called a triangular norm. It is very well studied and most often used in the fuzzy logic community. And in this lecture, we will look at triangular norms, their definition, some examples, and some geometric perspectives. Towards this end, we have seen that given two propositions, P and Q, a compound proposition could be made from them like this: f is continuous and f is increasing. Now the question is, when is the above statement true? This compound statement, which is a conjunction of two propositions P and Q, when is this true? We have seen that this is true if and only if both the component propositions are true. Now, how is this evaluation justified or valid? This is because we have this concept of truth functional evaluation, or this assumption, where we say that the truth value of a function of propositions essentially depends on the truth values of the component propositions. If we take the classical logic where the truth values are just 0 and 1 and look at the corresponding connectives there. So negation is the now familiar complementation. If you look at the truth table for the negation, it is essentially converting 0 to 1 and inverting 1 to 0. Similarly, this is the corresponding truth table for the classical conjunction. Now we have seen that in fuzzy logic we are essentially extending this truth value set from just the 0-1 to the entire interval 0. Now, we saw that if that were the case, then we could propose operations on just the unit interval 0-1, but having in mind that they should coincide with the classical case when we are looking at the vertices. What do we mean by this? If you look at the unit square, the classical connectives, they only specify the values at these endpoints. The classical binary connectives. And what we are interested in here is that we want to come up with a conjunction, which soon we'll denote by the symbol T, which is not just from the set 0-1 cross 0-1 to 0-1, but from the entire interval 0-1 to 0. That means we need to generalize this to the entire domain, to these points and also on the boundary, in such a way that it coincides with the classical truth table for conjunction on the vertices. Now, we have seen that using this generalization, we have proposed a few operations as possible interpretations of the conjunction when it comes to dealing with pairs of fuzzy sets. We also asked the question, why not other operations? So this led us to first discuss this question: how do we choose the operations? And we have seen that at least one way to look at them is looking at what are the theoretical structures that they could impose on the set of fuzzy sets themselves. This is an approach that we have studied quite well in the series of lectures last week. Now, in this lecture, we are going to look at another but related question. What properties of operations do we retain or extract? This is not just limited only to conjunction, but this will be the question that we will deal with, also with negations, implications, and distinctions. Now, let's examine this question a little deeper. Now, these are the three operations that we are familiar with. Henceforth, we will use the symbol T. The nomenclature, the symbolism will become clear presently when we introduce triangular norms. Now, if you look at it, what properties do we want to extract? What could be a good axiomatic definition for fuzzy conjunction? Towards helping us in that, let's look at these 6 properties. So, we need some boundary conditions to be satisfied, that is clear. And this is commutativity, associativity, idempotence, continuity, and increasingness in both these variables. It's a binary function, so by this symbol, we indicate that it is increasing in both the variables. Now, are we justified in looking at it like this? Let's look at the corresponding classical truth table for this. So the boundary conditions are clear, and we also see that it is commutative. We know that it is associative. What about idempotence? Yes, we have seen that that also leads us to a nice algebraic structure. What about monotonicity, increasingness in both the variables? Now let's look at this. Let's fix the first variable to 1 and look at moving from 0 to 1. So in this lattice, we know 0 is smaller than 1. So essentially, when you fix the first variable and move from 0 to 1, we see that it is increasing. So perhaps it is not unjustified to ask for monotonicity. Now, why monotonicity in both the variables? Because it is commutative. So if it is monotonic increasing here, then we want the same kind of monotonicity here also. So these are the properties that we are looking at now. So now, let's investigate each of these functions with respect to these properties. Now, it is clear that minimum satisfies the boundary property. And if you fix y and increase x, it is going to increase. So hence it is increasing in both the variables. It is also commutative and associative. We know that min of x comma x is x, so it is idempotent. And we know that it is also continuous. That means it satisfies all these properties. Now, if you look at the product, we see that it is satisfying the boundary conditions. 1 times 0 is 0, 1 times 1 is 1, 0 times 0 is 0. Once again, it is increasing in both variables, commutative, associative. It is continuous also. But what about idempotence? So now, by idempotence, we want that Tp of xx should be x. This implies x dot x is x, which implies x should either be 0 or 1. So clearly, we know that it is not idempotent on 0, 1. This is what we have now. Consider the final conjunction, which is the Lukasiewicz conjunction. We know it satisfies the boundary condition. If you fix y and increase x, it is increasing, so it is increasing in both variables. It's commutative, associative, we have seen this. We also know it is not idempotent, and as a polynomial in xy, it becomes continuous too. So when we see these, that among these 6 properties that we have seen, these 3 conjunctions, these 3 interpretations of conjunctions, they seem to satisfy almost all of them except for idempotence. But we should be a little careful, because when we are actually generalizing and coming up with the properties, we should ensure that we have a large catchment area of operation that we could consider for fuzzy conjunctions. So in this sense, let's look at continuity. Is it really warranted? To help us in that, let us introduce 2 more functions. Once again, the symbolism will become clear presently by the end of this lecture. So if we consider these 2 operations, and let's see with respect to these properties that we have. Now, to help us understand how this function TD looks like, if we were to actually look at the graph of this function, this is how it looks like. Now, notice that we are looking at functions from 0, 1 square to 0, 1. So the graph of this function will be contained entirely within the unit cube, 0, 1 cube. And now what happens here is, according to this definition, if either x or y is 1, then it is minimum. So essentially it is the other value, and that's what you see here. This is y is equal to 1. As x varies, this is what happens. This is when x is equal to 1. As y varies, this is what happens. And in the rest of the places, it is 0. So clearly, you see that this is not continuous. Is it idempotent? Clearly not. If you take TD of say 0.4, 0.4, now you see that 0.4, maximum of 0.4, 0.4 is not 1, which means this is 0 and not equal to 0.4. So it is not idempotent on the entire interval. So what it means is that if you look at this, of course, it satisfies the boundary condition. In some sense, it is increasing in both the variables. Even a constant function 0, we do not ask for strict increasingness. It is commutative, associative, but neither idempotent nor continuous. Now, what about the last function that we have there? Let's look at its graph. This is how it looks like. Now, once again, you will see that it is not continuous. Essentially, you are seeing that it has gaps there, and also that it is not idempotent. In fact, for the same value of 0.4, if you look at it, you see from the definition 0.4 plus 0.4 is less than or equal to 1, so it is 0, which means it is 0 and not equal to 0.4. So once again, we see that these two operations are neither idempotent nor continuous, which means perhaps idempotence and continuity are not the properties that you would like to put in an axiomatic definition of a fuzzy conjunction. So how is a triangular norm defined? So as a function from 0, 1 square to 0, 1, and we will use the symbol T consistently to indicate a triangular norm. We will call it a T norm for short and for brevity. A T norm is a binary function on 0, 1 which is associative, commutative, monotonic, and satisfies this condition. What is this condition? It essentially says that 1 should be the identity of this function. We don't have to worry whether it is left or right because it is commutative. Now, is this warranted? Why this generalization? First of all, if you look at the truth table for the binary conjunction, classical conjunction, you see here 1, 0 is 0 and 1, 1 is 1, which perhaps gives us this idea that perhaps we can ask for 1 to be an identity. Another reason which perhaps will resonate better with you now is for the kind of algebraic structures that we can realize on the 0, 1 interval with respect to T. For instance, later on we will see that if you take this set 0, 1 along with this function, which is a binary operation of 0, 1, we can see it is actually a monoid, a commutative monoid, in fact an integral commutative monoid. We will see these terms in detail in one of these lectures during this week itself. In fact, we could also come up with another operation called the residual operation with respect to this T norm, with respect to which we get a very interesting latticeal structure called the estuated lattice. Okay, so this is another reason why we could consider this as a valid or useful generalization. Finally, let's look at these 5 interpretations that we have got. It is clear all of them satisfy this property also. That is, 1 is actually an identity for all these operations. So perhaps we are not really unjustified in asking for this. Now, let's try to decode these 4 axioms and from a very geometric perspective so that we will have a visual idea of how these functions look like. Already we saw that the graph of a T norm will be embedded within the unit cube. Now, what does T of 1, x is equal to x mean? By commutativity, whether x is 1 or y is 1, the other value is the value that the function T will take. So when x is equal to 1, you see here as y varies, you get the identity function. It moves from 0 to 1. Similarly, when y is equal to 1, it moves as x varies, it moves from 0 to 1. So in the boundary, when x or y is 1, this is the value that the function can take. That means the t norm, it is an identity function when either x or y is equal to 1. Now, along with the monotonicity, let's look at what happens on the other boundary. So of this. Now when you look at this, we have this is the x-axis, with the y-axis, with 0, 1, 1. We have seen that on these two, it acts like an identity function. What happens here? That means what if one of them is 0? Let's take this, t of x comma 0. Now we know by monotonicity, this is less than or equal to t of 1 comma 0, which is actually 0. However, t is a function from 0, 1 square to 0, 1, so the smallest value it can take is 0, which means putting these two things together, this implies t of x comma 0 is 0, which is also the case with t of 0 comma x by commutative. So we see here that any t norm on the boundaries it is fixed. When one of them is 0, it is 0. When one of them is 1, it is the identity function. Now, what is commutativity? Commutativity says that it is symmetric about the diagonal. So if you look at this diagonal here, I've drawn it in 3D. Then we want the graph to be symmetric with respect to this axis. Now, what about associativity? Is there a way to understand it geometrically? Well, there are very well researched articles on that, and some of them even claim that associativity can be thought of as three-dimensional symmetry. Well, now let's look at some of these functions that we have. The first of them is the minimum function. Let's look at the graph of this minimum function, and let's keep these boundaries or the skeleton graph for reference. So if you look at the minimum function, the graph of that will look like this. So clearly it coincides on the boundary, and what is interesting is exactly on this axis it meets, because we know that it is idempotent. Min of x comma x is x. So along the diagonal, when you move along the diagonal on the xy plane, what you are going to get is the same value x on the z plane too. What about the product t norm? How will it look like? This is how it looks like. So if we imagine the line here, then you see that clearly it is symmetric with respect to that line there. The Okasiewicz triangular norm, T norm, it looks like this. Once again, you see it is symmetric and coincides on the boundary. But what you will also find is, compared to product and minimum, you see that even when the arguments are not 0, x and y need not be 0, however, TLP of xy can be 0. This is a point we will come back to in a few lectures later. Now, if you look at this function, which says that when one of them is 1, it is identity, rest of the places it is 0. Now, once again, trivially it is monotonic, it is associative and also commutative. But why this nomenclature of TD? If you look at it, as was shown, the minimum value that any t can take is actually 0, and wherever possible, this function has taken the value 0. It cannot take the value 0 on the boundaries of x is equal to 1 or y is equal to 1, because the definition demands that it should be identity. Wherever else it is possible to take 0, it has taken. So in that sense, this is really the smallest t norm with respect to pointwise ordering, and in that sense it was called the drastic t norm, and the symbolism that's got stuck to it is as D for the drastic word. Now, if you look at this particular function, which is again a t norm, the graph of it looks like this. We have seen this a few slides earlier too. This is essentially, this is your minimum t norm. All we have done is we have kind of put our foot on this and then smothered it down to the floor. So take the minimum t norm and then cut it down to 0. That's exactly what we have done, but along the opposite diagonal or the anti-diagonal. So this is how the graph of it looks like. clearly it is not continuous. You see that these points coincide also with the min graph. That means these are points on which idempotence property holds. Of course, as I said, we'll see this in detail a little later. We just wanted to have a graphical feel for these functions. As I said, this is the minimum, and all you are doing is smothering part of it onto the floor. Well, what about these axioms? Are they mutually independent? Well, whenever we come up with an axiom schema or axiom set, we want to ensure that they are not only minimal, but they are also non-redundant. So in that sense, we ask the question, do any of these imply the other, or do any combination of these imply the other? We will see that is not true. For example, if you take this function xy into max of xy, we will see that it in fact satisfies all the other properties of it. It is commutative, monotonic, increasing, and also if you take 1, 1 becomes the identity. Now, so here we see that this function does not satisfy associativity. It is neither commutative, but it is commutative and monotonic. And it also satisfies the identity property. If I take y to be 1, it is x into 1 into 1, which is x. Thus, it satisfies all the three properties of commutativity, monotonicity, and identity, but not associativity. And if you look at this function, it can be shown it is associative. Clearly, when it is not commutative, because when you take the value, let's look at for this particular function, let's look at the 0.4, 0.6. So it falls in this regime. Here it becomes 0. However, if you look at t.6.4, then we see that it falls under this regime where it is minimum and you get it to be 0.4. Thus, it is not commutative. Of course, it is monotonic, that can be seen. Now, let's look at this function. It is essentially the drastic t-norm, only that we have not smothered it onto the floor, but we have raised it to the level 0.5. Clearly, because of this, it is not going to be monotonic. For instance, if you look at t of 1, 0.4, it will be 0.4 somewhere, and suddenly it increases to 0.5, and so on and so forth. So it can be seen that it is not monotonic. Finally, if you look at this function, which is just a zero function everywhere, constant zero function, vacuously it is associative, commutative, and monotonic, but obviously one does not play the role of an identity. Thus, all these four properties are in fact independent of each other. They are mutually independent. Now, we have seen that among all these 6 properties that we considered initially, we saw there were many functions, t-norms, which are continuous and non-continuous too. However, we have seen that there is only one example of a t-norm we have seen so far, which is idempotent. Are there other t-norms which are idempotent? In fact, when you look at it, it can be proven that if t is an idempotent t-norm, then t really has to be only the minimum t-norm. So essentially it says that minimum is the only idempotent t-norm. Perhaps firstly this justifies why we did not ask for idempotence in the axiom set. Now, to prove this is very simple. The converse is clear because if minimum is idempotent, so minimum t-norm is idempotent. But let's now look at, let us be given an idempotent t-norm. So that means we have a t such that t of a comma a is equal to a for all a in the close to 0 1. Now we need to prove that this t is in fact min. That means we need to show that for any AB, t of AB is actually min of AB. So let's consider arbitrarily 2 values from 0. Now, we know that 0 1 is a totally ordered set, which means there is always an ordering between A and B. Let's assume that A is strictly less than B. Now, what could be the value of P of AB? Now we know that by monotonicity, this is greater than PA. Once again by monotonicity, this is smaller than P of A1. But P of A1, because 1 is identity, is actually A, and by idempotence we see that this is A, which means P of AB is sandwiched between A on either side, means P of AB is A. But what is this essentially? By our assumption, A is less than B is nothing but minimum of A comma B. And by commutativity, if B is smaller than A, similar argument can be given to show that P of AB is actually B. So that means P is essentially the minimum T norm. A quick recap of what we have seen in this lecture. We had seen different interpretations of fuzzy conjunctions. What we have done is a balanced extraction of properties into axioms. As we have seen, we did not ask for continuity, we did not ask for idempotence. Also, we did not just ask for the boundary conditions, instead we asked for 1 to be the identity. And the boundary conditions are automatically satisfied because we had 1 to be the identity and also because of the monotonicity condition. Finally, we have seen some geometric perspectives, some visual illustrations, because it's always good to have a visual idea of how these functions look like and what these properties mean visually. Now, where do we go from here? The rest of this week, we will look at T-norms from a little more algebraic and analytical perspective. We'll look at some algebraic and analytical properties which are very important for us going forward, especially in the applicational setting that we will be discussing. And we will also justify with the Lukasiewicz T-norm that we had seen earlier also, which almost came to giving us a lattice along with this dual operation. It's there. We see that it still holds a very special position. In the next lecture, we will start with the analytical properties of T-norm, different types of continuity that are available on T-norms. And for this lecture, a very good source, if you want to turn to, would be the book by Tillman Messier titled Triangular Norms. Thank you once again for joining me in this lecture and hope to see you soon in the next lecture. Thank you.